This tutorial looks at the offset to targets, which are constants with simple feedback loops. We're going to assume that students have viewed and understood the earlier videos in this analysis series, and here we're going to provide a number of tutorial questions so you can test your own understanding. The secret is you must read the questions and then pause the video while you attempt your answer. Please do not continue the video until you've made a genuine attempt at the answers, otherwise these tutorials will have little benefit for you. A little bit of background, just to remind you, we're talking about feedback loops of this form, very simple feedback loops with a compensator M and a system G, and we want to find the offset, which is the steady state value of R minus Y, and with these simple loops you'll see that's actually this signal E, and E can be defined using this transference here, E equals 1 over 1 plus Gm times R. Now a little reminder above, 1, we're only assuming step type targets, so R is going to be of the form A over S, and 2, you can only define offset, it's only meaningful if the loop itself is stable. If you've got an unstable closed loop, clearly the output will not converge. First questions then. Find the offset for the following system compensated target triples given that the closed loop is stable. So you'll see there's 4 different problems here which you can try, and what I want you to do now is pause the video while you read these and attempt them, and I will now continue looking at the solutions. So the first one, G equals S plus 3 over S plus 1 S plus 5, M of S equals 2, R of S equals 3 over S. And you remember we defined that E equals 1 over 1 plus Gm into R, and the limit as t goes to infinity of E of t is therefore the limit as s goes to 0 of S into, or S over 1 plus Gm into R of S. Now for all these examples you'll notice that we've chosen R to be something over S, and so that S will cancel with the S in the numerator, and so what you will end up with is 1 over 1 plus G of 0, M of 0 into whatever value of R of t you've got, which in this particular case is 3. So if I put in the numbers, what have we got? We've got 1 over 1 plus, what's G of 0? It's 3 over 5. What's M of 0? It's 2. And what's R of t? It's 3. So if I multiply everything up, top and bottom, by 5, what you're going to get is 15 on top and 5 plus 6 underneath, which gives you 15 over 11, which is quite a large offset. Next one, I've got G of S equals S minus 1 over S plus 1 S plus 2, M of S is 0.4, R of S is 1 over S, and I'm going to go straight to the formula in this case, which is 1 over 1 plus G of 0, M of 0, and in this case you'll notice the magnitude of R is just 1. So I get 1 over 1 plus minus 1 over 2, that's G of 0, times 0.4, that's M of 0, which gives me 1 over 1 minus 0.2, or 1 over 0.8. Next one, you'll see G of S, S plus 2 over S plus 1, S plus 4, S plus 0.1, M of S is 3, and R is 1. So again, we do our formula, 1 over 1 plus G of 0, M of 0, and what do you get? You get 1 over 1 plus 2 over 0.4 times 3. Now I can multiply top and bottom by 0.4, and so I get 0.4 over 0.4 plus 6, which hopefully you can see by inspection is 1 over 16. Next one, g equals 2 over s minus 1, s plus 5, m of s equals 4, and again r of s is a unit step. So again, doing my formula, 1 over 1 plus g of 0, m of 0 is going to give me 1 over 1 plus, now g of 0 is going to be minus 2 over 5, m of 0 is 4, so you get 1 over 1 minus 8 over 5. Multiplying top and bottom by 5, you get 5 over minus 3. Not very good at all. Question 2. Find the offset for the following system compensator target triples. So again, what you need to do at this point is pause and give these questions a go, and I will now continue with the answers. So you're given a reminder here. This question didn't tell you that the closed loops were stable. So the first thing you've got to do is check for stability. So I'm going to write down what the closed loop pole polynomial will be for this g and this m. So you've got 6 times s minus 5 plus s plus 1, s plus 5. If I multiply that out, you get 6s minus 30 plus s squared plus 6s plus 5, and what will jump out at you very, very quickly is this big minus sign. So this includes right half plane poles, this system. Therefore it's closed loop unstable, and there's no point talking about offset. What about the next one? Again, let's write out what the closed loop pole polynomial is. So we've got 2 times 3 plus s cubed plus 0.8 s squared plus 0.2s plus 0.1. And again, it will jump out at you. I hope you can use the Routh array. So if I do Routh, if it's not obvious to you, you can see 0.8 times 0.2 is less than 6.1 times 1, and therefore you've got right half plane roots. So again, there's no point doing offset with this example. Question 3. Find the offset for the following system compensator target triples. So again, you'll see there's 4 examples, and we'd like you to pause the video and attempt these before you look at the solutions. Question 1 then. So I've got s plus 3 over s plus 1, s plus 5, 2, and 3 over s is the target. Now the first thing to note here is we've included an integrator. Okay? And therefore the limit as s goes to 0 of 1 over 1 plus g of s m of s equals 0. So in other words, the offset equals 0 if closed loop stable. So that's the sort of observation that a student should be making before they start this. There's an integrator there, and so I'm expecting an offset of 0, but obviously I first need to check that the system is closed loop stable. So let's do the closed loop pole polynomial. PC equals 2 into s plus 3 plus s plus 1, s plus 5. If I multiply this out, 2s plus 6 plus s cubed plus 6s squared plus 5s, or joining common terms together, s cubed plus 6s squared plus 7s plus 6. And this is indeed closed loop stable. I can use the Routh to confirm that those poles are all in the left half plane. So the offset is 0. Next question. Again, you'll see there's an integrator. So the offset will be 0 if I'm closed loop stable. So let's find the closed loop pole polynomial. PC equals 0.4 into s minus 1 plus s s plus 1, s plus 2, which gives me 0.4s minus 0.4 plus s cubed plus 3s squared plus 2s. And what jumps out at you? We have this negative coefficient, so there is a right half plane root, or at least one. And therefore it's not closed loop stable, so you cannot calculate the offset. Next question. S plus 2 over s plus 4, s plus 0.1, and again you'll see the integrator. So this problem reduces to checking for closed loop stability. So the closed loop pole polynomial is 3 into s plus 2 plus s plus 4, s plus 0.1, which gives me 3s plus 6 plus s cubed plus 4.1 s squared plus 0.4, and joining common terms, s cubed plus 4.1 s squared, so there was an s there, plus 3.4 s plus 6. And again I can use Routh to show closed loop stable. And therefore the offset equals 0, because we have an integrator. Final part of question 3 then. So g is 2 over s, s minus 1, s plus 5, m of s equals 4. Again you see there's an integrator, so all we need to do is check for stability. So PC equals 8 plus s, s minus 1, s plus 5, which gives me 8 plus s cubed plus 4s squared minus 5s. And what do you notice? Big negative sign, so this has got a right half plane pole. This system, it's closed loop unstable, so I cannot deal with offset. Question 4, final question. And you'll notice that what we've done in this question is we've added a block in the feedback path to represent some form of sensor, which is fairly typical. And what we want you to think about is how does adding this sensor change the offset? Otherwise, the question is similar to all the others. We've given you that all the closed loops are stable, so you don't have to bother with that particular step, and you can focus on getting the offset. So I want you to pause now and try these, and we will go through the solution. First then, let's do some background. How do we deal with this situation where we've put h? What we really want is the limit as t goes to infinity of r minus y. However, we know that with an integrator, and if you look at both of these questions, you'll see they both included an integrator, then the limit as t goes to infinity of r minus w equals 0, or r equals w. So that we know, because there's an integrator. And we also know that the limit as t goes to infinity of y of t times h of 0 equals the limit as t goes to infinity of w of t. So what does this give us? It gives us the value we're interested in, I'll call it y subscript infinity for convenience, equals r over h of 0, or r minus y infinity equals 1 minus 1 over h of 0 into r. So this is our offset term if there's an integrator and the loop is stable. Okay, so let's just write that formula down so we don't lose it. So the offset is given by 1 minus 1 over h of 0 into r. And you'll notice here we've not done anything with g because it's got an integrator, it's no longer relevant. We've not done anything with m, it's no longer relevant. In fact, the only thing that we need is this h. Of course you need the g and m to ensure that you're closed loop stable, but in this particular case you're given that information. Now here, h of 0 equals 1, and therefore 1 minus 1 over h of 0 equals 0, and therefore the offset equals 0. And that's what you'd like. You'd like to choose your sensor to have a steady state gain of 1 to avoid problems. What about this next one? So again, you'll see it's exactly analogous scenario. So I'm going to ignore the G and ignore the M and write down my formula. The offset equals 1 minus 1 over h of 0 into r. But in this particular case, h of 0 equals 0.2, or 1 over 5. So you get 1 minus 5 into r, which gives you minus 4r. And you might say, that's pretty bad. But anyway, what that shows you is a poor design of sensor, or something else needs to be considered. So in summary, we've given you some tutorial questions on determining steady-state offsets for simple feedback loops.